Hello and welcome to Trusted Teachers, being the support we needed. Today's another computing flavoured input, and what I want to do is just look at the binary number system briefly, and as ever I'm joined by Mr. B.
Hello there.
Okay, so we're just going to dive into this, Mr. B. What we're looking at is a broad area called data representation, how we store text and images and numbers inside computers. And today we're just going to look at whole numbers. We're just going to look at integers they're called, but just for us it's just positive whole numbers. And dive right in. We use that's the decimal number system that we've been using since primary school, and we've been using all our lives. And just to break it down, and this will seem really obvious, but what we use is we've got these things up the top called place values, and we know we've been using our units, our tens, our hundreds, our thousands, so on. And if we have a number that I put in here, what that means is we get 3 lots of 1,000, 2 lots of 100, 4 lots of 10, and 5 lots of 1. 3,200 and 45. 3,245. That's how the decimal number system has been working for us for a long time. Computers can't use the decimal number system. Computers have to use the binary number system because essentially at the heart they're made up of switches, which can either be on or off, and we use those two states, 0 and 1, and we represent them by binary 0 and binary 1. So we use zeros and ones because computers don't use decimal at all. They only use ones and zeros. So the place values when it comes to binary number system is slightly different because it's not base 10. This here is what we call base 10. It goes up by a factor of 10 each time. Ones, tens, hundreds, thousands. So it's going up by a factor of 10 each time. 10,000 with the next one. In binary, because it's base 2, we start with 1, but it then doubles each time. It goes up by a factor of 2. And this is, I really like this wee table here because you can't forget it. It's so easy to remember. As long as we start with 1 at the right hand side, then all we're doing is doubling the numbers. 1 becomes 2, becomes 4, 8, 16, 32, 64, 128. And we stop at 128 for our purposes today. Excuse me, you can go further, but we only want to deal with 8-bit binary numbers. So binary numbers have just got 8 digits, and then we've got 8 place values here. Okay, so we can use this table to convert between binary and decimal numbers really, really easily. So we'll dive right in and look at this one here. So in this example, we needed to find the binary equivalent of 41. And what we've done here is we've not used 128 because that's too big. We only want to find 41. And we've not used 64, again, because it's too big. We can use a 32. And basically, we're building up these place values to get to our target value of 41. So we've used a 32. We can't use the 16. 32 and 16, as we all know, is 48. And again, it's too big. So we'll just put a 0 in where we're not using these place values. And we put a 1 in where we are using them. So 32 plus 8 would be 40. And we can add a 1 on at the end. And we put zeros in if we're not using them, as I said. So the binary equivalent of 41 becomes 001, 01, 001. Excuse me, and that's it down there. So we're just reading that from the table from left to right. And it just becomes 001, 01, and 001. So if we type 41 at a keyboard, what the computer does is it does this exact conversion and it stores 41 in its memory and in its storage systems in the 8-bit binary number 001, 01, 001. Okay, so binary to decimal. If we take the bit, this is going the other way now. Okay, so we're taking a binary number and we're converting it to a decimal number. So what we have here, again, is our binary number is in the bottom row here. And we're doing exactly the same we did before in opposite. If there's a 0, yes, we can ignore it. If there's a 1, then we can add it together. So we've got the binary number and we're trying to find out the decimal number now. So I would say we've got 001, so we've got a 32 and a 16. So that's 48. We've got no 8s, no 4s, but we've got a 2, that's 50, and a 1, So I would say that number there, 00110011, is actually 51 in decimal. So that's how we can use this wee table to go back and forward between binary and decimal. Okay, a couple of activities now for Mr. B. I've got a couple of numbers here for you to do a wee conversion for me, Mr. B. What I want you to do is use that table and take 10 and convert it into binary and 16.
Okay, so I would go 00001 to get the 8.
0, 1, yep.
Then 0, 1 to get the 2, 0. So it's the 8 and the 2 added together.
So what we're saying there is that would then be 00001,001. Is that what you got?
16 would just be 000010000.
Yeah, we don't need any other ones under any place values except 16 is one of our place values. So 0001,0000. That's exactly correct, Mr. B. And I think we might have another activity to now find out the decimal numbers that these two numbers represent here. I think I can hear you frantically working away.
Oh, sorry, I was I was muted. It would just be 2 because the last placeholder is 2. That's the only one that's got a value in it.
If we take these numbers and put them under our place values, 0000010, so the 2 has a 1 under it. So that is just the number 2 in decimal, yes. And the next one there, Mr. B?
That would be 15 because the last 4 are filled in. So 8 plus 4 plus 2 plus 1 is 15.
4 plus 2 plus 1 correctly is 15. So that's exactly it. That's really good and quick kind of picking that up, Mr. B. Okay, so here's an actual exam question now. So this is what pupils were faced with in an exam a few years ago. Convert the following 8-bit binary number into, I've used the word denary there because that's what the exam question used. Denary is and decimal mean exactly the same thing. So we're taking that number and working out the decimal. Do you want to go at that exam question for me, Mr. B?
Okay, I don't have any paper in front of me, so I'm just going to use my phone. $183.
183, spot on, yes.
The only ones I didn't add were 64 and 8.
64 and 8, they weren't added. So it's 128 because there's a 1 at the first place value. No 64s. Then 128 plus 32 plus 16. Quite right, there's no 8, but plus the 4, the 2, and the 1. And that gives us 183. So what a computer would store in its memory and storage areas would be 10110111. That to us means 183. Okay, that's just a kind of brief introduction to the binary number system, converting between decimal numbers into binary and binary back into decimal. We're trusted teachers, being the support that we need. Thanks for joining us.